Well, welcome to Lecture 5 of my General Relativity course. I should say Mathematics of General Relativity. I am doubtless not doing the physics justice here, but I want to talk in this lecture about observers, and I want to try to dig into a little bit more of how would you formulate an observer mathematically in the Euclidean context, and then I will sort of leave the question open as to how we should do that in the Minkowski context. But anyway, let's get started here. So this is just kind of really digging into the question of what do we mean by an observer? You have some context of what we mean by an observer in physics. It's like there's this way of setting up measurement of time and distance relative to an origin, right, in three extended spatial directions. And of course you can talk about the technology to make that happen, clocks and lasers and various conventions of signals and so forth. But what I want to describe first here is actually a formal version of Newtonian mechanics that I learned from my PhD advisor, Dr. Fulp of NCSU. I think I first saw this stuff in a course that he taught called Math 430, Mathematical Models in Physics. And I know he's working on a book that has these things in it, and so maybe that'll be available sometime soon, I don't know. But anyway, that's just one small part of a larger course, but the basic idea is here. What formalism do you want to use in order to handle the concept of an inertial observer, right? It's basic to Newton's laws, the idea of an inertial observer. Newton's laws are written with respect to an inertial coordinate system. So what is an inertial coordinate system? How do you judge a coordinate system to be inertial? These are questions that we should ask. Actually, thinking deeply about that question ultimately is one of the things that led Einstein to general relativity. We'll talk a little bit more about that as we go on here, okay? But so here's the definition to start with. We say E is a Euclidean structure on a set S, if and only if E is a family of bijections from S onto R3. All right, so the idea here is to think of S as perhaps physical space, right? And R3 is a mathematical model of that physical space. And, so if space itself is Euclidean, then there exists a bijection between physical space and mathematical space, at least in principle, right? And here's the rules we insist on for these bijections. We insist that if you take the composite of one and its inverse, you get a rigid motion in the sense it's a translation and a rotation of R3, and that if you take any one of these bijections, right, and any rigid motion, then the composite of a rigid motion and X is again in Euclidean structure. That's kind of a maximality condition. So here's a picture of what's going on, roughly speaking. And so, of course, if you've had manifold theory, you'll kind of recognize what's going on here. And I have no doubt that part of the reason Dr. Fulp taught this was to prepare his students, in part, for later courses in manifold theory. Maybe that was part of the motivation, actually. But anyway, so it's Euclidean structure on a set S. Well, I just read that, didn't I? So if we have a pair S and a Euclidean structure, that's called the Newtonian space. And again, here rigid motion means it's the composite of a rotation and a translation, right, like that. And here's a picture. So physical space, perhaps, R3, Y composed with X inverse goes like this, right? The first shall be last and the last shall be first. So X inverse goes like that from here to here, and then Y comes back down there, so we go from here to here again. So Y composed with X inverse is a mapping from R3 to R3, and we insist that it actually is a rigid motion in the sense defined over here. All right. So what's an observer in this language? An observer is a function from some subset of the reals, thinking of this as time, into the Euclidean structure, where basically for each time you assign one of these bijections. What this is a time-varying coordinate system on S. So for each t in I, we denote x of t as x sub t, and this is a a bijection here from S to R3. All right. So when I had this course, it was actually very eye-opening for me because I had labored, without realizing it, under the idea that R3 was physical space, and that's a philosophically damaging idea because you need to separate in your mind the mathematical model of space versus space itself, philosophically speaking, in part so that you can imagine different possibilities, right? It's because if you insist that physical space itself is R3, then when somebody proposes it's something else, then you have to completely change your idea of what reality is, and that's kind of annoying. On the other hand, if you're a little bit more laid back about this and say, well, there's this thing called reality, and we have mathematical models which describe some aspect of it, then it's a little bit less taxing when you have the idea that maybe you need to let go of that mathematical model and endorse a new one, Because after all, physical space, well, this is my philosophy anyway, physical space, whatever it is something far more sophisticated than any of these mathematical models we have to describe it. Even general relativity, it's just, a little bit better, perhaps, than Newtonian mechanics, but still it falls short of capturing whatever that true reality is. Again, I'm really making more of a philosophical claim there than or maybe metaphysical claim, I guess it would be. But anyway, given a material particle which moves through S, if it is at gamma of t, at time t, in S, at time t, then gamma, a path, right? It's mapping from R to S, is called a trajectory of the particle. And if you have a particle, you can look at its trajectory. You can calculate, with respect to a given observer, you can calculate the position, the velocity, the acceleration. And this gets underplayed sometimes in introductory physics, but it is an inescapable fact that position, velocity, and acceleration are always made with respect to an observer, with respect to a choice of coordinate system, right? And so that immediately begs the question, what are the allowed coordinate systems, right? So, because you can quickly find out that if we measured position, velocity, or acceleration of a trajectory with respect to a different coordinate system, right, then we get a different velocity, position, or acceleration. So if we're going to talk, if we're going to compare results for different observers, then how do these compare? These are natural questions that we should ask when we're thinking about position, velocity, and acceleration. All right, so given the mathematical sophistication available for introductory physics courses, we don't delve too deeply in that direction. And given the general disinterest of mathematical courses in physical observables, we generally ignore this question altogether. So unless you're a physics major, you probably haven't really thought that much about these questions before. But here's how you could do it in a somewhat systematic way. So here it goes. So again, position is just the observer, it's this. So gamma of t is a path in S physical space. X of t is a path in R3. So you're making a bijection between the path in physical space and the corresponding path in R3, all right? And by the way, paths in R3 are what we study in Calculus 3, right? Now you might have thought, well, I studied paths in physical space in Calculus 3. Well, yes, you did so under the assumption that R3 is physical space. Have you thought about that? Anyway, so velocity is the derivative of position, and acceleration is the derivative, the second derivative of position, which of course could also be written as the derivative of velocity. So we can compare position, velocity, and acceleration of a trajectory with respect to an observer x versus an observer y, right? Now, since y composed with x inverse is a rigid motion for each time, that means that there exists a rotation at each time and a translation at each time, such that we can write the rigid motion as the multiplication of the rotation and the translation like that. So in short, the formula, right, the formula which relates the x position and the y position is this. Well, here it is in gory detail. Of course, if you want to drop the of gamma of t, you could just write it like this. And if you wanted to be even more lackadaisical and drop the t dependence, the explicit t dependence, you could write like that, right? So the position in one coordinate system is the position in the other coordinate system rotated and then shifted, all right? Now here I'm comparing two different observers, all right? So the rule is two different observers, well, let's see here. Yeah. Yeah, you can go downstairs. The brothers are not going to watch you? Oh, I think the hoverboards are out of batteries right now, buddy. So, sorry, I'm in the middle of something, okay?
Last time I went out and I checked the hoverboard and they still had
I
batteries.
think I heard the hoverboards go beep, 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 beep. I think they're out of battery right now.
That was a different one.
That was a different one. Well, why don't you go ride the hoverboard then?
The brother wouldn't watch me.
Well, you should go ask them again.
Well, they still won't.
Well, you should go ask again. They'll help you.
But they'll just say no.
Well, maybe you should make some soup. Maybe some casserole in your kitchen. That would be good.
What's casserole?
Maybe you could make me some cappuccino in your coffee maker.
What's cappuccino?
You got to go figure it out.
Oh.
Yeah.
That's great.
Yeah, you should go do that. Or you could just swing in that hammock if you'd like.
Swing in it? But Matt said I couldn't.
Matt said you couldn't swing in the hammock? I think he's wrong. I think you could swing in that hammock a little bit.
Well, only
All right, sorry guys.
Only we can just do it at Alabama, but not at
You can only swing in Alabama, but you can't swing here? I think you could swing here too.
I think it's because this one is my one.
It's the same.
No, the other one goes way more upper. The difference is only lower.
Oh,
That's the point.
that's the point?
I mean, that's what it is, but
Maybe you should go draw a picture maybe.
I don't see like one of those things. I don't see like with my home.
Oh, I'm sorry. Well, Benjamin, I'm going to have to go back to my video now. Is that okay?
That's okay.
Okay. So, we have position in the y coordinate system versus position in the x coordinate system is related like so. Now, I think that, okay, yeah, so we do insist that, so this would rule out like curvilinear coordinates, for example. It's a little windy. Have to be, again, the coordinate systems are just shifts and rotations at each time, right? But then when you look at how the velocities are related, Benjamin, buddy, I need you to stop doing that. Well, just don't kick the thing, okay? If we look at how the velocity is related, when we differentiate this, we notice we have a product rule because r could depend on time, x could depend on time, so we get like r dot x plus rvx, and then derivative of the shift, all right? So this is how velocities are related. And then if we differentiate again, this gives us the relation between the acceleration of one observer versus the acceleration of another observer. Now here we're still looking at somewhat general observers. We'll soon give a definition of an inertial observer, all right? So like for our inertial observers, the accelerations will match. But here, for a more general, x versus y, we could have, as you can see, the acceleration in one system doesn't have to match the acceleration in the other, right? And so if r was constant, right? See how this formula would work? If r is constant, that would be 0, this would be 0, and you just have rax plus p double dot. By the way, this means second derivative, this means first derivative, yeah. Anyway, let's go on here. We have number 3. So, Benjamin has left us. All right, so the equations relating position, velocity acceleration between observers were x and y. X and y were, where are the observers? Oh yeah, where the observers could be non-inertial. But Newton's laws concern inertial observers, and so we need some more definitions to make that precise, all right? So if you had a trajectory, then you can say that the particle is in a state of rest relative to an observer x if the mapping defined from the interval to R3 given by, we're mapping t to the position of the trajectory at time t. If that's constant, then it's at rest, right? In other words, relative to x, the position vector gamma is not changing. Likewise, the particle experiences uniform rectilinear motion relative to observer x if and only if the mapping, the path from t to the position of t the position of the trajectory at time t, that actually describes a straight line in R3, right? So also, the particle experiences a force relative to observer x if and only if the particle is neither at rest nor in a state of uniform rectilinear motion. So a different way of saying this would just be saying well, no, let me just leave it at that. I'll leave it at that. All right. So the definition above focuses on the properties of a particle. In contrast, the definition which is below is going to talk more about a special kind of observer, namely an inertial observer. So here it is. An observer from time intervals into the Euclidean structure is called an inertial observer if and only if there exists a fixed time-independent observer, x naught, all right, and a r in SO3. This is a rotation matrix, and v and w in R3 such that x of t is equal to, you rotate the fixed observer, the fixed observer's position, and then you add t times v plus w. So what it's saying is an inertial observer is related to a fixed observer just by a particular rotation paired with a constant velocity shift is what this is. All right, because here v and w are not functions of time, they're just fixed. Okay, a particle is called a free particle if and only if it experiences no acceleration relative to an inertial observer. So, again, when we look back here, these observers didn't have to be, like, if one of them was inertial, the other one didn't have to be, okay? Like, if x is inertial, there's no reason that y has to be inertial because, we can have all these, here the r and the p are functions of time, and like p is a function of time, like this p essentially is being played by tv plus w over here. So, I mean, that's a function of time, but simply so, right? So, like, let's see here, how can I say this? To get an inertial observer, like I say, if you start with inertial, like if x is an inertial observer, and you want y to also be an inertial observer, you need that r dot is 0. All right. You need that the rotation matrix in question is not changing, and you need that p double dot is 0. So you need that p is just equal to vt plus w. All right. So again, if you start with an inertial observer and you want to make sure that your new observer is again inertial, you would need to rotate it by a constant matrix and shift it by a non-accelerating shift. All right, so like p double dot have to be 0. All right. Now, all right, so theorem. If x is an observer and y is, they're both inertial observers, then there exists R, a rotation matrix, and v and w vectors such that x of t is equal to r times x of t, such that y of t is equal to r x of t plus tv plus w for all t and I. Moreover, if a particle experiences no acceleration relative to x, then it experiences no acceleration relative to y. So now we're starting to build up the concepts we need to state Newton's laws. All right. Now, I think this theorem actually makes a pretty decent homework problem. So I'll try to put that in there for you. So let's review Newton's laws from physics, basic introductory physics, right? What are they? Newton's first law, in its usual kind of classical language. Every material remains in its state of rest or in its state of uniform rectilinear motion unless compelled by forces acting on it to change its state of motion. Newton's first law. Newton's second law. The time rate of change of the product of mass and velocity of a material body is proportional to the force acting on the body, and it takes place in the direction of the straight line along which the force acts. It's a version of Newton's second law. All right. Newton's third law. The forces two bodies exert on each other are always equal and opposite in direction. This is the existence of action-reaction pairs, right? So, Dr. Folk, in his course, he made the following observation, that Newton's first law, it's almost like, or the first and the second laws, like, depending on what you start with, like, what are they really saying? I mean, well, he says this, the first law can be understood to say, from our way of thinking here, there exists an inertial observer, all right? There exists an inertial observer. It's because if there exists an inertial observer, right, then if a particle is in a state of rest or uniform rectilinear motion, then it is. it is already in that, and it's going to stay in that unless there's a force, right? Second law, time rate of change of the product of mass and velocity proportional to the force acting on the body takes place. So, I mean, this is, if the mass is constant for the body, right, this just becomes F equals ma. So, anyway, I don't want to delve too much further into that. There's a lot you can say about what do those laws really say or not say, but let me just look at some calculations here. So the formula pages on pages 2 are very interesting, and they're seldom seen outside a physics course. Let me go back to the formulas on page 2 here. Page 2. Here's the formulas on page 2. This, and this, right? If we put r dot being 0 and r equal to the identity, in other words, we're looking at two observers that one is not rotated relative to the other. It's just that their origins are shifted basically by p. So p is like, you translate one origin to the other by p. Then the velocities are just equal to each other plus the velocity of the origin. and likewise the accelerations are equal, except that you also have to shift by the acceleration of the origin, right? And so when I teach introductory physics, these are the transformation laws that they get to see in the introductory course, because I can't really be talking about rotating coordinates in introductory physics. But now, however, it's interesting to note that if you study these formulas, right, then if the rotation between your observers is not constant, right, if you're not dealing with inertial observers, but you have one observer which is inertial, right, and another observer which is non-inertial, it can be the case that r dot is non-zero to get from the inertial to the non-inertial. And in that case, your velocity transformation rule, it can also include this piece here. In other words, like we see this when we study rotational physics. Like this would be like the omega r kind of, kind of term. We get a tangential velocity from a rotational velocity at a particular radius kind of thing. And so this would be, I think if you dig down into this could be like the, let's see here, try to think how to say this. Maybe this would be analogous to the, like, alpha, how's it go? When we use rotational physics, we talk about omega, and we talk about alpha, the rotational acceleration, the angular acceleration. I think you could tie this into like an angular acceleration. This would be something like, I'm trying to think what the word is for this one. Whew, I'm a little rusty here. I don't quite remember, but I know that part of this is what goes into what we call the Coriolis effect, and the other part would be what you would either think of as centripetal or centrifugal, depending on how you want to slice things. But well, anyway, that seems like there's a formula you see in physics in terms of like the angular velocity omega, and these things can be rewritten a lot if you talk about the rotation in terms of its axis, and then like the so there's like a theorem. Any rotation in 3 dimensions can be written. There exists an axis, right, which it's the rotation around. So like any rotation can be written as a rotation around a particular axis where the plane perpendicular to that axis is fixed, right? So any rotation can be written as like a rotation by an angle theta around some axis, and then theta dot will essentially tell you how fast that rotation's going, right, around the axis, and theta double dot would be the rotational acceleration around that axis. So you can reformulate this kind of thing in terms of the rotational velocity and the rotational acceleration, and so forth. So this is not how this formula looks like in physics. The way this formula typically looks in physics is quite different, and if I can find the right level of discussion, I'll make that into a homework problem for you, because I think it's interesting. And it's one of those things that not every introductory physics book really does justice to, but the Coriolis effect and the every book talks about centripetal acceleration for sure, but the Coriolis effect is a little bit more. So the question then is, what does it mean to have an inertial observer, right? Like, philosophically, how do you tell that you have an inertial observer, right? I mean, you can check whether or not 2 inertial observers are inertially related, right? I mean, if there exists if there exists a fixed time-independent observer, such that you can get to from your inertial observer to this fixed time independent one by a fixed rotation and a non-accelerating shift of the origin, then okay, then you've got inertial observer. But how exactly do you get this fixed time independent observer in nature, right? Well, I mean, you can do this. If you have two observers in nature, right, then you could compare them, right? And if you can get from one to another by a formula like this down here, right, if you can get from y to x by just rotating by a fixed matrix and doing a non-accelerating shift, then, okay, well then those two inertial observers, those two observers, you could say that they're inertially related. But the thing is, if they're inertially related, but they're also actually subject to the same like underlying acceleration, you wouldn't really be able to tell. Like you could imagine like, you know, two giant elevators, so to speak, right? And they're both accelerating upward with the same acceleration. And then like you could, have one rotated and the other, and they're, it's shifted up a little bit. You have one here, one's up and shifted up, and it's up, it's a little bit rotated, but they're both going up, at the same acceleration. Well, the coordinate systems relative to those two accelerating elevators would be inertially related, right? Because it's just, because they have the same acceleration relative to an actual inertial system, which in this case would be like the tabletop. So having different coordinate systems and showing that they're inertially related, all that would really show is that those different coordinate systems share the same underlying acceleration relative to some other coordinate system, right? How would you decide then that your coordinate system really is genuinely inertial? See, that's done for us here through the mathematical formalism, but it begs a physical question. How do you find an inertial observer, right? And this question ultimately was part of what drove Einstein to relativity, thinking about thought experiments with people in elevators and like how would you tell the difference between being in an elevator versus being under gravity. Like you can, think about an elevator in space or whatever outside the context of like Earth's gravity, and you can create the same accelerating effect that you get from just, sitting on the surface of the Earth and being pulled by gravity towards the center of the Earth in the Newtonian sense. So if you can create the acceleration of gravity, right, by just putting a elevator in space and making it go, then why should we think that gravity on Earth is any different, right? Maybe gravity itself is just a frame effect. It is a quote-unquote fictitious force. So fictitious forces, what's a fictitious force, right? So a fictitious force is like one which is arising. It's all right. So like you say MAY equals to the net force, okay? And then in that viewpoint, everything that M times all these things you think of as forces, right? But M times these things are not actually forces, except possibly maybe this piece. So if there actually is a genuine non-frame related force, like a spring force perhaps, something like that, then there'd be that, right? But then there's all these other terms which are appearing mass times these terms, y. Well, just because the y coordinate system is accelerated relative to the x coordinate system. And so those have sometimes been called forces in classical physics, like the centripetal force or the centrifugal force, or the same thing, different perspective, but or the Coriolis force. See, there's not genuine forces. What they are is the apparent force, which is coming from an accelerated effect of the frame. In other words, when we use fictitious forces in physics, what we're really doing is we're going past the proper boundaries of our formalism. Like Newton's laws are supposed to apply in inertial coordinate systems. That's their home. That's where they belong. So inertial coordinate systems is where Newton's laws are most logical. And then if you try to do Newton's laws in non-inertial coordinate systems, sometimes you can adapt them, right? You can kind of make adjustments to them by adding some sort of fictitious force to account for it. So in introductory physics, we do Newton's second law in circular motion is ma equals to mv squared over r or something like that. Or sometimes we'll account for, more than that. Like there's the centripetal acceleration, there's also the tangential acceleration, and but anyway, what I'm trying to get at here is just that there are sometimes extensions of Newton's laws which we teach in introductory physics, which, to be fussy, they're not really Newton's laws proper. They're an extension of Newton's laws to, other coordinate systems. And depending on how you parse the language, you can find yourself calling things which are really just consequences of using non-inertial coordinates. You can find yourself calling those forces, like, again, the centripetal force, the Coriolis force. All right, I think I said enough about that for now. So, anyway, all of this, so I just wanted to share with you because I think I really enjoyed this myself as I think it was the first semester that I was a double major in math and physics. I was doing this. I could forget. I'm not sure exactly the semester, but I think it was. This semester after I dropped electrical engineering, I had this course. And I found it really interesting, this way of formalizing classical mechanics and coordinate change in terms of a rotation matrix and a shift and the derivatives thereof. It's nice. But and also the whole idea that an observer, right, is a mapping from time into Euclidean structure, and the pair of physical space and Euclidean structure is what we would call Newtonian space, perhaps. So wonderful. What about Minkowski space? Do these ideas work out for Minkowski space? What would a Minkowski structure be? Well, that I can describe a Minkowski structure. All right, that I can do. Oh man, my paper is getting more and more wet. It's raining out here. My markers are going to start smudging just from the moisture in the air here pretty soon. So formal Minkowski space, we say H is a Minkowski structure on a set S if and only if H is a family of bijections. All right, from physical space-time to R4, such that if you take any two of these bijections, then Y composed with X inverse is a composition of a Lorentz transformation and a space-time translation. In other words, it's the analog of a rigid motion, right? It's either a rotation and a boost and a translation in time and space. Or two, if you have the composite of one of these bijections and a Lorentz transformation and space, in other words, something like I was just saying, composite of Lorentz transformation, space-time translation, then phi composed with X is again in this family of bijections. So in 2, the formula I'm talking about, of course, is just phi of P is Lorentz matrix times P plus Q, right? Where we have, and I want to insist it's one of the, I probably should even put the upper arrow on that, just to be, I would suspect that if you dig further into this, you want to put the proper orthochronous, Lorentz transformation, and Q is the element of R4. So then the question is, all right, so this is a Minkowski structure, right? Fine. What's an observer in this context, right? See, I'm not actually sure how to answer that question. I mean, it was clear to me. It's clear to me that the idea of an observer in 3 dimensions, right? Like it was the, I'll go back again, observer for a Euclidean space. It just, each time, man, where'd it go? I'll find it eventually. Give me a second here. All right, so yeah, page 1. An observer is a function, right, from some subinterval of time to Euclidean structure. Each time you give a coordinate system, right? Well, we definitely can't do that anymore because there's no overarching universal concept of time in Minkowski space, right? Like, time is not separate from 3 dimensions. It's mixed together with it. So, like, how would I define an observer here? Like, what would an observer be in this context? So, I'm not sure what to say there, actually. I don't know how to adapt the discussion that we were having in Euclidean space to this new context. I'm not sure what to say about that. And sorry to leave it kind of open-ended, but that's just where I am. I mean, I thought about it a little bit, and I haven't quite figured it out yet. I'm not sure what to say. So anyway, if you've got an idea, feel free to leave it in the comments. So, thanks.